Welcome to STA 3301 Statistical Models. This lecture will cover all the materials in Module 3. My name is Namul Kobir and I am one of the statistics lecturers at the School of Mathematics, Physics and Computing. So this is the first part of Module 3. The Module 3 is basically model selection and checking. Model selection means if we have a regression model y equal to y1 plus y2 plus up to yk, that means k independent variables. Now, model selection, this means that what variable should be included in the model, either all of the variable or some of the variables. Model selection techniques will help us how to determine the number of variables that should be included in the model. And checking that means, as we know, that the error term, there are some assumption of the regression model, especially this is basically x1, x2, xk, especially x1, x2, xk, these are completely independent. These are the assumptions. And the other assumption is that the error term is normally distributed with mean 0 and variance sigma square. So we need to check whether these assumptions satisfied or not. The relationship between the response variable y and the independent variables x are linear, at least approximately. So that means y equal to x beta. That means x1, x2, x2, xk plus e. The relationship between y and all of this x is linear. The independent variables x are not highly correlated with each other. So x1, x2, xk, they are not highly correlated. The residuals EIs are uncorrelated, normally distributed with mean 0 and constant variance sigma square. So if we take a sample, for example, this is the regression model, and we got the data from this, the population data, and from here we got the sample data, and here is the model, and we got the E. So that means this is the error term here. Similarly, we take the another sample, we make another error term here. So that means this error term, this is a random variable, and it comes from a population. That means the distribution of this error term is normally distributed. That means population mean of this error term, expected value of E is 0 and variance of E is constant sigma square. So that means this population, the variance is always constant. Whatever sample you are taking, that the error terms should have variance sigma square. The uncorrelated and normally assumptions imply that the residuals are independent random variables. Normality assumption of residual is required for hypothesis testing and interval estimation. Now, criteria for selecting of regressors for best model. This will be discussed in this module. Procedures for model selection, model adequacy, residual analysis. That means, first of all, how we can calculate the residuals, and then how we can check the assumptions are satisfied or not. And if the assumption does not satisfy, for example, if the constant variance assumption does not satisfy, then we need to use another technique that is called weighted least square that we'll discuss in this module. And we also discuss the other diagnostic checks, especially other check to check the assumption, especially if there is any outliers in the data set. Then there are some diagnostic tests where we can determine if there is any outlier in the data set. And multicollinearity. Multicollinearity, that means if x1, x2, xk, these variables are highly correlated, then we call them multicollinearity. And we can check whether this is the highly correlated or not. In this module, we will check that. Two contradictory criteria. We should include as many regressors as possible for useful prediction. In view of cost involved in collecting data on a large number of regressors variables, it is desirable to include as few regressors as possible. Simpler models are also preferred in other grounds. And so we need to do the model selection. There are a number of methods available in the literature, and no method is better than others. In some cases, well-thought personal judgment is necessary for the final decision regarding which regressors should be kept in the model. One of the criteria is the coefficient of multiple determination. Sometimes we call this R square. The formula here, this is the regression SS, regression sum of square of regression, and this is the sum of squares of total, the total sum of square. And we can write this as a 1 minus sum of squares of error divided by sum of squares of total. So if we fit a regression model, we can easily calculate the sum of squares of regression, sum of squares of total. If we divide this, we will get the R square. The positive square root of R square is called the multiple correlation coefficient between y and the regressors x1, x2, xk. That is, R is a measure of linear association between y and all of the explanatory variables in the model. There are some problems in R, especially inclusion of new independent variables or regressor increase the value of R square, although the new regressor is insignificant. Therefore, one must be careful in considering the addition of a new regressor in the model just because it results large R square value. One way to guard against the overfitting of the model due to increased R square value is to introduce a penalty term, analyzing the inclusion of new variable unless they make a valuable contribution. One way of this using that is called adjusted R square. Here is the formula for adjusted R square. It is 1 minus sum of square of error divided by n minus p divided by sum of square of total divided by n minus 1. If you calculate this, this will be 1 minus n minus 1 or 1 minus R square. So that means once we get the R square value, we can easily get the adjusted R square. So adjusted R square is more useful than R square because R square always increase if you include a new variable. But if you include a new variable that is not contributing that much, then the adjusted R square will give a penalty term. Normally we calculate adjusted R square by using the computer statistical package in R. For example, I will show in a minute. If there are k star possible independent variables, there will be 2 to the power k star possible regression models. For example, if we have a model of 3 independent variables, then we make it 2 to the power 8, 2 to the power 3. That means 8 model. Let's say the independent variables are x1, x2, x3. That means the first model is only x0, second model is only x1, third model is only x2, fourth model is x3, and the next one is x1, x2, x1, x3. So similarly, we will get 8 variable. 1, 2, 3, 4, 5, 6, 7, 8. So we'll get x1, x2, x1, x3, x2, x3. So we'll get the 8 independent variables. So now we need to calculate the adjusted R square for each of these 8 independent variables. If there are 3 independent variables in the model, then we need to calculate the adjusted R square for each of this model, where SSEI is the sum of squares of error for the ith model. The particular model with the largest adjusted R square could be selected to be the best model. Now look at the example here. Fit all possible models. For the body fat example, probably you can remember we have discussed this in module 2. Calculate the R square, adjusted R square, and comment on which model appears the best. So we need to calculate all possible models. So in body fat example, I think we have 3 independent variables, so we'll get the 8 model, and you can calculate the R square and adjusted R square for all of this 8 model, and you can determine the best model based on the highest R square value. So in this example, I'm going to show. Look, here is the model is only one independent variable, and it shows how we can calculate the R square and the adjusted R square. So now let's say I am going back to my R code and I will show you how we can calculate that. So look at, here is the body fat data set. Here is the body fat data set. So let's say read that data file, and that's the VF. So this is the model here, full model here, and we can calculate the everything. So let's say if in the full model, just if we write here summary of that full model R square, this will give us the R square value is 0.80. And if we just write here adj dot r dot square, then it will give us the adjusted R square value. So this is if we include all of the variables in the model. Now if we include only x1 variable, the new model is bf.lm x1. That means only include x1 variable here. The adjusted R square is 0.71, and the adjusted R square here is 0.69. So now if I go back here, look at here 0.71, you can use the formula, you will get the same thing, or you can directly use the R, and the adjusted R square is 0.69. Yeah, if we include only one independent variable. So similarly, you need to calculate R square and adjusted R square for all of the 8 variables, and you can select the best model. So look at the interpretation here. The coefficient of determination R square is 0.711, suggests that the trip's skin fold thickness, that means x1, explains about 71% of the variation in body fat. The adjusted R square is 0.6950, suggests that this figure may be slightly lower. So now look at this data set, all the 8 variables here. We have just include only one variable, that one is that this is the R square value and the adjusted R square value, and we have also shown that this is the R square value and the adjusted R square value if we include all of the variables in the model. So look at which model is better. So we are looking for adjusted R square highest value. So let's look at the model here. This one is 75, 75. Probably this is the not say. So this model is 3. This one 5, 6, and 8. These are the better model based on the adjusted R square. But look at here, 76. This model include 3 variables, but model 3 include model 3. This one 7. Model 3 include only only one variables. X basically one independent variables x2. So based on this, we can select any of these, but look at model 3, probably the better one, because it is simple, only include one variables. And the look at here, in some cases, you can get the negative R square value. These negative results have no direct interpretation other than being close to 0. Negative R square values indicate a model with a poor fit. We are interested in finding the best model, the model with the highest R square. So based on this case, we can select that this is the probably our best model, because this is a simple model, only include one independent variable. There is only one included variable, but in model 8 we have seen here all of the 3 independent variables. As with many decisions in statistics, choosing the best model is particularly a subjective decision. So you can choose any one of this model, either model 3, 5, 6, 7, or 8. But in my opinion, model 3 is the best because it is the simple model, and the adjusted R square value is not varying that much. Second criteria is called the mean square residuals. Mean square residual is just the SSE divided by n minus p. So SSE here n minus p is the residual degrees of freedom for model I. So that means we need to calculate MSE for each of the model and then select the best model with the lowest MSE. As SSEI and MSEI decreases as the number of regressors in the model increases, but it may also increase if the reduction in SSE due to the addition of a regressor to the model is not large enough to compensate for the loss of 1 degree of freedom in the denominator of MSE. The most appropriate model is the model with the lowest unexplained variation per degree of freedom. That is the model with the lowest MSE. The smallest MOC occurs when SSE is small, n is large, and p is small. So look at the case here, all of this model here. Here is the, if we include only x2 here, for example, in that case, the number of parameters is 2. Here is the SSE and the MSE. So how we get the MSE? Let's say if I go back to my R, MSE, look at here, SSE is the sum of squares of residual. This is the SSE, and if you divide by this one, SSE divided by SSE divided by, according to the definition, if you divide this by n minus p, you will get the MSE. N minus p, you will get the MSE. So n minus p, if I divide SSE divided by n minus p, n here is 20, p is it depends on particular model. Let's say in the model you have only 2, so if p is 2, then in this case we will get the second one. 71 should be in your, oh no, sorry, SSE is okay. It's not the case. Basically, SSE, it should be this one. Is MSE. So I think I have that on MSE somewhere. MSE. This is the MSE. This is the MSE. So if I we are here, adjusted R square. Okay, adjusted R square here. So okay, this is the MSE. So if we include only one independent variable x1, and this is our R square adjusted, and this is our MSE. MSE, this is the MSE of the full model. That means if we include all of these, let's say in our case, all model include only this model is bf dot lmx1, and in that model we have only one independent variable. So this is our MSE. That means x1 model. So if I go back to our in the x1 model, the MSE here is 7.9511. Should we have that below 7 point MSE? If I write here MSE, see, this will give, oh sorry, MSE, this is 7.9519. So this is how we can calculate the MSE. So once we fit the model, we can easily calculate the MSE. So we should prefer a model that has lowest MSE. Again, based on this, we can see that MSE here is 6 point. This is the this one, or that one. Look at this is the full model. This one is little bit lower, but includes 3 but this model only include 1, but the MAC is quite low compared to this. So that we can choose this is the better model based on the MAC. Now the relationship between adjusted R square and MAC. So adjusted R square is this the definition of adjusted R square. If we plug in the R square here, SSEM divided by SST, ultimately we are getting 1 minus n minus 1 SST MAC. Thus, the value of M that minimizes MAC is the value that maximizes adjusted R square. So that means for any particular model, if MAC is low, that means for that model, the adjusted R square will be high. Another particular criterion is called the CM. M is the number of regressors, and here CM definition is SSEI divided by S square. SSEI is the sum of squares of residual for model I, and M is the number of regressors including X0 in the model, and S square is the mean square error from the full model. So let's say in the previous example we have full model is X1, X2, X3, basically X0 as well. So that means that S square is for the full model. Even if you, let's say for any particular model X1 only included X1, in that case you need to use for that model sum of squares of error for that model divided by S square is for the full model minus n minus 2m. 2m is the, for example, if you include only x1, then the number of m is 2 because only x1 and x0, x2. And we know that this S square is a reliable unbiased estimate of sigma square. Okay, so for any model, we need to calculate the CM statistic, and if CM equal to M, this indicates of adequate model. So that means the select the subset of a best model with lowest CM value about equal to M. Equivalently, they select a model where CM minus M is approximately 0. So we need to calculate CM first, then M. If the difference is close to 0, we need to select the best model. Now this is how we can calculate CM. So look at by definition, this is sum of squares of error divided by S square. S square is the full model, that means sigma hat square for the full model, minus n minus 2m. So for the body fat example data, let's say how we can calculate that one. So let's say I am going back to my R code. MSC1, so probably not, no, I am deleting that one. Okay, so in that model here, let's say the model that included only x1. Now I am going to calculate the S2. S2 is the sigma square estimated value of sigma square. This is for the full model, that is the MSC for the full model, that means S square. Now SSE is the sum of residual, sum of squares of residual. This is the sum of squares of residual. If we calculate this one, this will be the residual of that model only included x1 and sum of squares of residual. So we'll get the SSE. And M is the number of parameters. So for example, in that case, this is our model. If we take the coefficient length of that, we'll get the number of parameters in that model. And CM by definition, look at by definition, this is SSE divided by S square. So sum of squares of residual. So this is our SSE divided by S square minus this is our n, length of residuals is the n, minus 2 star m. So if we calculate that one, we will get the CM value. CM value. So if this is for the only include X1 model. So the M value is, if I write here M value is 2 and CM value is 7.27. Now if I go back to our model, so we need to only X1, and this is CM and this is M. The difference is this. So similarly, you need to calculate CM and M for all of the models and select the best model based on if the difference is 0. So look at, this is the perfect model. Basically this will happen if we include all of the variables. We will get the CM is and the difference will be 0. But on the other hand, look at the model 3 and model 6. The difference is, this is the closest one. You can either choose this one, x0, x1 and x3, and in model 3 only one variable x2, but here is x1 and x3. So you can choose any one of these, but in my opinion I will select this one, because here this is the simple model, only include one independent variable x2, and the difference is not big. There is the difference between them is not that much. So according to this definition, CM minus M, we can choose model 2 is the model 3 is the better model. That means the model that only include x2 variable. Another one important characteristic is called the Press statistic. Press means prediction error sum of squares. When the main purpose of regression analysis is to predict the future response or estimation of mean response, the regressor should be chosen in such a way that mean square error of prediction is the minimum. Now, how we can calculate that? The Press statistics for any given models works like this. For the data set of regressors in the given model, feed the given model and compute the predictions of each observation. That means y I hat. Then omit observation j from the data, denote that yj, and repeat the model to this reduced data set. That means total observation minus one observation yj. Using the repeat model, predict the missing value yj. If the model is good, then you should expect that the difference between them should be close to 0, or they are very similar. Then compute the difference and then square, and repeat step 2 to 5, 2 to 3 for each of the j. Then calculate sum of yj minus yj square for model I. The steps are preferred for each model I, and a Press statistics computed for each model. The model with the smallest press is preferred. So that means you need to fit each model first and then calculate the Press statistic, and then the model you can select that which has the lowest press. So according to the definition, look at the definition here. EJ is the error residuals minus 1 minus HJJ. Look at what is HJJ. HJJ is the Z diagonal element of the hat matrix. So this is the hat matrix, and Jth diagonal any elements of the hat matrix is the HJJ. And this is always 0 to 1. For any j value, the HJJ between 0 to 1. Select the subset of regressors for which the value of Press statistic is smallest. Okay, so look at this previous example here. We have 8 model. Let's say we are dealing with the model X1, and we can calculate how we can calculate the Press statistics. But before that, look at the definition of Press statistic is something like that. Sum of that means you need to first calculate the H, this one, and the diagonal element, and then sum of residuals EJ divided by 1 minus HJJ square. So let's say I'm going back to R and show you how we can calculate that. let's say in the R we are dealing, let's say I am going to show you only for one model, that is the model with only only one independent variable, only one independent variable x1, only one independent variable x1. I can show you from here. Let's look at this. These are the head values you can get from here, or let's look at the this is. I will show you in both way. First of all, look at here. So we have CM, we have AM. So now press. So look at here. By definition, look at definition is there sum of residuals EI minus 1 minus head values. So in R, basically if you just write here in this model is vf.lmx1. If I just write here vf.lmx1, it will give us the head values. So if I just write here head values bf dot lm x1, that means the model include only one variables. So these are the head values here. The first one is 0.12024. Similarly the last one, so we have 20 observation, we'll get the head values here. So Peirce statistic is, according to the definition, is that sum of residual, that means EI. So this is our EI divided by, look at the definition, EI divided by 1 minus HJJ. 1 minus HJJ. So this is our 1 minus HJJ is the head values of that model. If you calculate that, you will get the Peirce statistic. So now if I write a Peirce, the Peirce statistic 177.78, we will get the Peirce statistics for only included x1. We will get the Peirce statistic 177. Well, it should be 177.81. It should be 177.78. It should be 177.78. You can check this. I think this is wrong. 177.78. So similarly, you can calculate the Peirce statistic for each of these model and then select the best one with the lowest PSE. So in this case, look at here, lowest we can get here. I think this is wrong, but for let's say this is correct, but this is wrong. So if you can calculate this one, the lowest one is set to 77, 97. Look at this is the best model. This is that model. That means using Peirce statistic, model 3 against appears favorable. The model 5 to 8 all would use similar Peirce statistics. So model 3 is the better model, on include only x2. So this is the Peirce statistic. Another important criteria is called the Akaike information criteria, or AIC. This AIC acknowledges that fitting more and more covariates can only reduce the residual sum of squares and MSE and hence increase R square. The AIC introduced a penalty term to discourage the introduction of unnecessary covariates. The AIC is defined as AIC equal to minus 2 log likelihood plus 2p, where log likelihood is computed for the fitted model and based on a normal distribution here. And p is as usual the number of parameters in the model. Within this definition, models with a smaller AIC are the better model. So look at the example here. This is the AIC value. Now if I go back to my R, how we can calculate the AIC value? So just calculate the AIC. So for example, this model is only x1. If I calculate the x1, X1 model, the AIC value should be 102.11. 102.11. So again, this is wrong. 102.1. Hang on, I think there's something. I gave 102.11. What about 177. Oh, 102.1. I think this is AIC. So in the study book, this is wrong. You can check with that, and this value should be press. So AIC value. So based on the AIC, look at this, the AIC value, and this is the model 2 is the best based on the AIC. This is basically AIC. So the model with the lowest AIC here is 97. So that is the best model. This is basically AIC, not press. And based on the press here, we can see model 3 is 134. This is the lowest one. So this is the best. So based on both press and AIC, model T that includes only X2 covariate is the best model. So out of this 8 model, we can see model T, that means include only X2, is the best model in respect of both adjusted R square. CM minus AM is almost close to zero. It has lowest press and it has lowest AIC. So we can select this is the best model. And just look at here, this is not AIC value, this is basically press value in the study book. I think this is wrong. You can calculate this, and the previous table, the press, basically this is not press, this is basically AIC value. Okay, so that's the part 1. So in part 1 we have discussed how we can select the best model based on adjusted R square, MSE, press, CM minus M, and AIC. And in this particular example, modified example, we select model 2 is the best model in respect of all of these criteria.